Okay, so we will pick up where we kind of left off. Up here, got this Excel document. And work through these with you. So I believe this was everything, how it downloads. Okay. So last class, we worked through how we do one population examples in Excel. We have a sample mean and we have an unknown population variance. I'll show you an example of how we would work through a proportion example today. And then I'll introduce the first type of example that we have for two populations. And I'll talk more about that when we get there. Two populations to make a little more sense as we work through an example. So last class, we were looking at kind of this average, age that first smoked e-cigarette. The data also had this variable, just whether or not the individual has used e-cigarettes before, right? So these are middle high school kids. 1 if they did, 0 if not. So I've got this 1, 0 variable. We said to find a sample proportion, it's really just the sample mean. So we'll use that average function, but a special case where I'm finding the sample mean of a 1, 0 variable. Okay? So I'll find the average of this 1, 0 variable. And what this is going to tell me is the proportion of individuals in the sample who have used e-cigarettes, right? So I get about a proportion of 0.33 or 33%. So I'm going to use this hypothesized true value, and we're going to set up a right-tailed test, okay? So the idea there is I want to test for whether or not this true proportion now is greater than 0.25. So I'll assume the opposite is true, which is that it's less than or equal to that. So I've got a greater than sign in my alternative hypothesis. So here I've got a right-tailed test. Okay. So I believe if we think about that distribution of sample proportions, it should be centered around whatever that true proportion is, although I don't have the true population proportion, but I have an assumed true population proportion of 0.25. I found a sample proportion of about 0.33. I forget exactly what it is in Excel, but it's about 0.33. So if I think about for a right-tailed test, my p-value would be the area to the right of the sample evidence I found. Now that doesn't really help me until I turn that sample evidence into a z-value, right? Or into a test statistic, a z-statistic, since it's coming from a standard normal distribution. So I'm going to turn this into my test statistic or z-statistic here. I can then use my standard normal distribution table to find the area to the right of that test statistic. That was kind of the steps that we've been doing. We could also find critical values, which I'll kind of show in a second, but for now, let's just focus on the p-value. So the equation that we have to give us our test statistic or our z-statistic here is we'll take our sample proportion, subtract the assumed true proportion, and we then divide by the standard deviation of our sample proportions, which we calculate by taking the assumed true population proportion times 1 minus that, and then over our sample size. Okay. So when we go to Excel, this test statistic equation, we don't have a built-in function, but we can use Excel to be our calculator. Okay. So that's what we're going to do. We're going to first find that test statistic. So let's go here. And also, I think I had some errors here. So what should the alpha, I think I deleted it on accident. I think this should have said alpha. What should the alpha be for a 90% confidence level? Yeah, 0.1, not point. I think I had 0.01 on that Excel file. I will play around with the alpha. I think that's why it was, because I was changing it and kind of saying, well, what if alpha changed? But we'll start out with it being matching up with that confidence level. Test statistic, all I'm going to do is basically use Excel to be my calculator. So I'll take that sample proportion minus that assumed true proportion. I'll put that value in a cell so that I can just click on it. I don't have to type these values in. I can click on these cell references. That way, if things change, everything will automatically update. I'll then divide by the square root of that assumed true proportion times 1 minus that assumed true proportion, and then divide by my sample size here. Okay. So all I've done is gotten this entered in to Excel using Excel to my calculator. There's no built-in functions. It's just like you would enter this into a calculator, except for so the values, you're just clicking on the cells that have the values in them. Any questions at this point? Okay. So you'll notice I have a sample size of 100, but that's not actually right. So I've got way more than 100 observations here. So we'll play around with this. So let's start out with using the actual sample size. So we'll use that count function. All right, that's what gives us our sample size. We'll go over Control Shift or Command Shift on a Mac, hit the down arrow, and then hit Enter. It'll send us back up to the top. So yeah, we got like almost 19,000 observations here. So we're going to go through this example using this sample size. And then once we work through the example, I'll show you why it's not very interesting. And we'll change the sample size to think about, well, what if we did have a smaller sample, just like a thought experiment. So why is this really high sample size not a very interesting value? Well, because even seeing small differences, right? So let's say instead of 0.25, maybe this was like the hypothesized true value was 0.3. Well, we found sample evidence that would be pretty close to that. However, our test statistic doesn't matter how close we are in terms of the actual values, it's how many standard deviations away is that sample evidence, right? And you can think about if I've got really high sample sizes, what's going to happen to the standard deviation of my sample proportions here? It's going to go down. If my denominator is getting smaller, my test statistic is going to be really large. As my test statistic gets larger and larger, that p-value gets really, really small. We know that we reject when p-value is less than alpha. So really high sample sizes, it's going to be really easy to reject, right? In fact, our test statistic with a sample size this large, we're 29 standard deviations away from the assumed true value. I mean, I think hopefully at this point, we're starting to get kind of used to certain numbers and kind of thinking about what are like reasonable test statistics. This is a wildly large test statistic, right? 29 standard deviations away, the table only goes up to 4, right? And so we're thinking about finding the p-value. If we were to do this by hand, well, the table stops at 4, right? The area to the right of 4 is like almost 0. So the area to the right of 28 is like almost even closer to 0. But in Excel, I can actually use the function and I can actually figure out what this area is for a test statistic that's larger than 4. So how would I do that? Well, I know the area that I have in my tail, right? Or sorry, that's the area that I want to find. The problem is, now that I've got this test statistic of about 28, I can tell Excel to tell me the area to the left of that, right? That was that norm.s.dist function. It's going to take this z value and give us the area to the left. The problem is I wanted the area to the right, so I'm just going to have to do 1 minus that. Okay. So I'll go to my Excel file, and I'm going to say, okay, norm.s.dist. Here's my z value, my z statistic. I want to find the area to the right of it. Well, this function will tell me the area to the left when I put comma 1, right? I always use that comma 1, always make it cumulative. We then said we wanted the area to the right, so we would have to do 1 minus that. So for this right-tailed test, I can use that norm.s.dist function, but I then have to remember, oh yeah, that gives me the area to the left. I want the area to the right, so I have to still subtract it from 1. Any questions there? Like I said, this should be really, really close to 0 because this is a huge test statistic. And sure enough, Excel doesn't even use scientific notation here. It's so close to 0, it just says it is. Right? Now, technically, you could go out to some ridiculous number of decimals and find something, but it is essentially 0. So our rejection decision should be pretty easy. We always reject if the p-value is less than alpha. So here, I'm clearly going to be rejecting, right? 0 is less than 0.1. But we can use this if statement so that once we start changing things, it'll update accordingly. So this if function, we kind of took a first look at last class. We first said, what do we want to check? Well, we want to see, is this p-value less than alpha? If that is true, I want to put the word reject in here. That should be my decision. Comma, if that's not true, that's the second thing that I'm going to tell it, then I put in the word fail to reject. right? If the p-value is not less than alpha, well, then I would fail to reject. So I'm just using that rejection decision as what I'm checking to see if that's true. If it is, then I put the word reject. If this isn't true, I put the word fail to reject. So here we should be seeing the word reject. Right? If a p-value of 0, it's definitely going to be less than alpha. Now, what if instead we want to use that critical value approach? Well, I should probably make the screen bigger here for you guys. So I'm going to be looking up a z value. We're dealing with proportions, so we can use that standard normal distribution. And I want to find the critical value that gives me alpha total in the tail, or the threshold number of standard deviations away, that if I see a test statistic that's even further than this, right, or really what I'm saying, if my sample evidence is a further number of standard deviations away than this threshold I'm setting, then I'm okay rejecting. So how do I do that? Well, I can use the standard normal distribution. If I know the area to the right of this z value is 0.1, well, when I go to Excel, just like if I were to go to the table, I only can use the areas to the left. So the area to the left is just going to be 1 minus alpha, right? Or in our case, 1 minus 0.1 or 0.9. I want 0.1 in the upper right tail, but I have to use the area to the left when I'm using those built-in functions in Excel. Okay. Now, before I even do this, what do I know is going to be true about the critical values for a right-tailed test? They should be, what is my standard normal distribution centered around? 0, right? So the area to the left and the right of 0 is 0.5, right? It's a symmetric distribution, exactly splits it in half. So I want an area smaller than 0.5 in that right tail. So my critical value should be positive, okay? Now, just adding that in there so we're thinking about these things. But basically, I'm going to take that norm.s.inv now. I'm working in the inverse. I know the area I want in my tail. It's going to be 0.9 or 1 minus alpha, right? So I'm just going to make sure I put in 1 minus alpha so that if I change alpha, everything will automatically update for me. Okay? So this should give me that critical value, 1.28. Well, my critical value of 1.28, where would my test statistic be? Well, my test statistic was what, 28 or whatever, right? It's going to clearly be in my rejection region, right? So very clearly, it looks like I can reject here. But if I remember more generally, doesn't matter if I have a left, a right, or a two-tailed test, if the absolute value of my critical value is less than the absolute value of my test statistic, we said then we're okay rejecting. Really all we're saying there is, if the sample evidence I found is a higher number of standard deviations away than the threshold number of standard deviations away that I've set, then I'm okay rejecting. It means it's very unlikely for me to see this. Now, when we're doing with a right tail test, we don't really have to worry about the absolute values here because the values are all positive. Now, if it was a left or a two-tailed test, we'd want to make sure we're using that absolute value, just like we kind of did in the examples that we did on Monday. But here, if I don't have to type them in there, why waste the time? So if I've only got positive values for a right tail test, absolute values of positive values doesn't change anything. So I'm just going to check to see here if that critical value is less than my test statistic, just using that built-in if statement again, comma, if that's true, put in the word reject. If it's not true, comma, put in the words fail to reject. So you can use this if statement to put in these rejection decisions using either approach. You don't have to do both of them every time. I'm just showing you both to show you that they'll lead us to the same decision. Okay? So we could use the p-value or the critical value approach with these kind of built-in if statement. And we should be getting the exact same rejection decision. Okay? So we'll hit enter here. Sweet. Both say to reject. Okay? Any questions over anything? You want to see a cell again? Or what if something changed? Or okay up to this point? So this isn't a very interesting example. right? Because this test statistic is so large, we can reject like almost any. You'll get start to play around with this value up here. Can I reject 0.28, 0.3? Oops, if I put it in the right cell, 0.3. Test statistic still huge. What about 0.32? Well, now at least I get a p-value that's not 0, even though it's 0.000007, right? But what about, can I reject that over like a third of these individuals have used e-cigarettes? Well, at the 90% confidence level, I can. Not at the 99, right? My p-value is a little bit too high here. If I instead change this to a 99% confidence interval with an alpha of 0.01, I'd fail to reject that the true kind of population proportion of kids, high school, middle school students who use e-cigarettes, I can't reject that it's less than or equal to 0.33. But all these other values, right? 0.3, 0.24, or I think 0.25 was the original one. We very clearly can reject. Okay. So notice if I use cell references, I can change this hypothesis test. I can change my alpha values, and everything updates as well as my rejection decisions here. Okay. Any questions? And I just don't know confusing. I was just kind of saying if we had different tests, we could change things and come up with rejection decisions pretty quickly. What if instead of this huge sample, and I kind of alluded to this earlier, but remember, here was our test statistic equation. What if I took a smaller sample size, right? What if I found the same sample evidence, right? 0.337 or whatever it was as our sample proportion, but it came from a much smaller sample size. Well, if I have a smaller sample size, this denominator here, the standard deviation of my sample proportion goes up, right? I get more variation in that sample proportion I can see. This is the idea. If I take samples of size 1, well, I could see things all over the board, right? And so it could be a very skewed sample from what the population proportion is. So if I've got a smaller sample, that standard deviation of my sample proportion goes up. This denominator is larger. My test statistic is actually going to be smaller, right? I'm dividing by a larger number. So if I've got a smaller test statistic or Z statistic, if this is getting smaller, it's going to be less likely it's greater than the critical value. It's less likely that I can reject the null. So we'll see what this looks like. So if I have a smaller sample size, I should be getting a smaller test statistic. So let's say instead we had a sample size of 100. Okay. I mean, we don't, but let's just say we did for the thought experiment here. Notice the test statistic falls dramatically, right? We still saw the same sample evidence, still the same hypothesis test, but right, it's just not near as reliable of a sample proportion because we have such a much smaller sample size. Okay, and so we don't want to, if we have a smaller sample size, it's not as reliable. We'd be less confident in rejecting the null hypothesis. Sure enough, I can still reject at the 90% level, but notice here, I'd fail to reject at that 99% level with an alpha of 0.01. Okay. So that's just a thought experiment about what happens if the sample size changes. You can kind of think about how it's going to change your test statistic. Because we're using the test statistic in our rejection decision, that's going to make it, depending if I have a higher or lower sample size, make it more or less likely that I reject the null, even seeing the same sample evidence, same sample mean or same sample proportion. Okay. I'll change this back to the original alpha here. Any questions on anything there? Do you want to see a cell again, or any general questions there before we kind of move on to two populations? So I'll post this after class. I'll probably replace the original completed file just so that the completed file looks exactly like the one that everything that we did in class. Now, the one thing that I'm not going to work through in class today, but it's included on this file is going to be the known population variance sheet. I use like a BMI variable here, found the sample mean. I had a known population variance given to me, found my sample size. I've got this two-tailed test, or actually, I'll change this. I think I have it mislabeled. So it looks like I'll go in. I think I had this set up as a two-tailed test, even though I had it labeled as a left-tailed. So I'll make sure I update this so that it kind of matches up with the labeling matches up with how it was worked through. But really it'd be the exact same steps of what we did just now with the proportion. The only thing that would change is this test statistic equation, right? Our test statistic for a sample mean with a known population variance is going to look more like when we had a sample mean with a sample variance. So that test statistic equation is going to look kind of more similar to that example. But when it comes to finding the p-value, the critical values down here, well, if I've got a known population variance, I'm going to keep using that standard normal distribution, just like the example today that we used for a proportion example. Okay? So it's kind of a mashup of the two. Kind of going to be a little bit more focused. That next Excel assignment, which I'll probably post next week after Monday's class, we'll have worked through enough where you could start kind of chipping away. I'll probably have one example of a one population Excel problem, but then the rest of it will all be two population, which we're just now going to start. Okay. So two populations. Oops. I want to minimize this. So I've got kind of the slides here and the, these functions that match up with what the Excel file has, just kind of a summary of what functions are used to find what. But we're now going to look at two population examples. So we're going to keep doing confidence intervals and hypothesis testing. I think the results are going to become a little bit more interesting than with just one population, but we're going to have a few more moving parts. But the principles and the steps of what we're doing, exactly the same. Okay. So the types of examples that we're going to have is we're no longer thinking about, okay, where is like the true mean retirement age, right? I take a sample and okay, it's not exactly equal to that. Can I reject them? No, right? Or can I build a confidence interval for where the true population mean retirement age is? What we're now going to do is something like, I've got two countries, and can I say that the mean retirement age in Canada is different than the mean retirement age in the US? So I'm going to be looking at the difference between two groups means. Now I can't see the population means, but I can get a sample mean from both groups, right? So we're gonna have three situations, that kind of a setup where I'm looking at the difference in sample means, and somehow I know the population variances. We'll start out with these examples today. They're kind of naive. If we don't know the population means, we probably don't know the population variances. But if we somehow had them, this is how we would work through it. We'll also look at the more practical scenario where we're looking at the difference in sample means, but we only have sample variances, or we don't know the population variances. And then we'll look at the difference in proportions, right? This is like, you can imagine some like political polling stuff. We could do like the difference in the proportion of people who are going to vote for candidate A versus candidate B, right? So it starts to become a little more interesting. We can make some more interesting conclusions. We also can do hypothesis testing for the same three sort of examples. We're going to have the same three tests, right, left, two-tailed, so nothing's going to change there. The only thing that's going to change, all the steps are going to be the same, is that our equations to find the confidence intervals and our equations to find our test statistics are going to have a few more moving parts in them, okay? And then we'll eventually get to match pairs, but that's not next week. That will be like probably the Monday after next week. And those are kind of interesting, but I'll hold off on talking about those until we actually get there. So my motivating examples to kind of give you an idea behind what we're doing is maybe I want to build a confidence interval for that true difference in starting salary is between econ and theater majors. So I take a sample of econ, take a sample of theater majors, find the sample means. I want to build a confidence interval for where the true difference in those salaries is. All I have is the sample means, so how can I do that? I might want to look at two time periods, the proportion of people who are in favor of the Affordable Health Care Act in 2011 versus 2010. Did that proportion go up? Did it go down? Right? Is it the same? Maybe I've got texters and non-texters response times. Is there a difference in the response times of people who are texting while driving versus not? Right? These are all, motivating questions. We can actually figure out what the true difference is in response times here, the true difference in starting salaries, the true difference in, proportion of people who find a certain policy favorable. So I'm going to build this out for us, kind of piece this together, and then we'll kind of come back. So what are we doing here? So let's think about, we want to find the difference between two groups means. Okay. So let's think about what the distribution, all we have are the sample means from both groups. So maybe this is like, I'll keep it general. So group 1 minus group 2. And we want to know, what's the distribution for that difference look like? I know what the distribution would look like for each sample mean, but what's the distribution of that difference look like? Well, let's think about the distribution of just each group sample mean. So I would have, maybe here's my theater majors kind of average starting salary. We'll call them group 2. Okay. So actually, sorry. So this is group 2 is going to be kind of our theater majors. So their distribution should be centered around whatever that true population mean is. And then the variance should be, for group 2, would be the original, hold on. The variance for the sample means from group 2 should be the variance of the original data we sampled from over our sample size for that group. All right? This is just one population stuff. We then could think about, okay, here's my first group. They have a slightly higher population mean. So the sample means for group 1 will be centered around whatever the population mean for that group is. And then the variance for those sample means from group 1 will be the variance of the original data we sampled from over our sample size. Okay. So if I think about what is the most likely outcome or the most likely sample mean I see from each group? Well, for group 1, the most likely value that I see is actually that population mean. And the most likely outcome for group 2 would be their population mean. So what's the most likely difference I'm going to see? Well, if these are the two most likely values that I see from each group, then the most likely difference I see will just be the difference between those two. Right? And so if I'm thinking about graphing out the distribution of my sample means, the most likely outcome for me to see would be whatever that true difference between the population means is. Okay? And then, these values are a little bit less likely. These values are a little bit less likely. So here's the probability I see those differences, and, less likely and less likely. And so really the probabilities of seeing differences further from that most likely difference, which is just the difference between the two most likely outcomes from each group. As I move further from that, the probability starts to decline. So what ends up being true is if I have sample sizes over 30 or original data that's normally distributed, I know my sample means will each be normally distributed. The difference between those sample means also is normally distributed. And it's centered around whatever that true population mean difference is. And then the variance for that difference, right? The variance for the difference in the sample means will just be each group's variance added together. So we'll have here the population variance for group 1 over its sample size, population variance for group 2 over its sample size. And if I wanted the standard deviation, I would just take the square root there. Okay. Well, now we've got a normal distribution. I can start to take certain values, turn them into z values, and find the probability of seeing these different sample mean differences. Okay. So now everything's going to be exactly like what we were doing before. It's just I've got two of everything. Right? So let's think about what we were doing with confidence intervals for one population examples. We had our sample mean. We based our confidence interval around that. That was the best guess that we had of where the population was. We then went a certain number of standard deviations away to get our upper and lower bound. And the number of standard deviations we go would be whatever gives us alpha total in the tails or outside of our confidence interval. So alpha over 2 on each side. Well, if this is the number of standard deviations away I need to go, I then multiply that by whatever the standard deviation is of the statistic I'm interested in. And there we had the original variance of the data we sampled from over our sample size. The same setup, the same principles will apply when we do confidence intervals for two populations, right? When we're looking at the difference in sample means. It's just that we're no longer going to center our distribution around one sample mean. We're looking at the difference in sample means. So that's the statistic we're interested in. It's composed of two statistics, right? But that is what we're interested in, that difference. Okay. If we had known population variances of the original data, just like with one population, we can keep using that standard normal distribution. Okay? So we'll find the number of standard deviations the way we need to go. But then now we need to multiply by the standard deviation of the statistic that we're interested in. So the standard deviation of the difference in sample means, which earlier we said was, well, the variance is just adding up each group's variance over its sample size. So if I want the standard deviation, it's just going to be the square root of that. So each group's variance over its sample size added together. And then to get the standard deviation, we would just take the square root, right? Because the variance is adding those two up. Standard deviation, we have to do one more step, which is take the square root. But the principles behind what we're doing is exactly the same. Take the sample evidence that we're interested in, no longer a mean, but the difference in means, go a certain number of standard deviations away. You know the population variance or variances here, so I can use that standard normal, and then multiply that by whatever the standard deviation is of the statistic that we're interested in. So at this point, right, I'm going to have all this information given to me in the problem. So this is, or if I calculate this from some Excel file, so I'm going to be able to plug values in here. The only additional thing I need to do is then look up that z value. So it's the exact same steps behind what we were doing before with confidence intervals. We just have twice of everything, except for the z value, I guess. So I kind of already outlined all of this, right? That difference in sample means is going to be centered around that true difference in the population means. The standard deviation we kind of talked through, and I can use that in order to construct my confidence interval. So we'll work through a couple of examples here with some actual values. Are any questions up to this point though, before we kind of jump into a few examples here? Might make a little bit more sense once we have some numbers to put to this. Okay, what did I do? There we go. So here's our general steps. Identify the piece of information that we're given, look up that z value, and then it's just a matter of plugging things in, doing the computation in our calculator. Okay. So let's start out with this motivating example of theater and econ majors. Actually, we can keep using the same sheet. I'll make it easy. So let's say I've got, 40 econ majors. So here my sample size for econ majors is 40. I find a sample mean for these econ majors of 45,000. And I have this known population variance for econ majors of 9,000. Theater majors, I've got 50 of those, it looks like. Their starting salary I found was 33,000. And the variance that's given to me for their population variance was 6,000. So I'm just writing down what the problem is giving me here. If I want to build a 95% confidence interval, what should alpha be? So alpha is just the percent outside of my interval in decimal form. Yep, so 95%, 5% outside in decimal form is 0.05. Okay. So at this point, I'm just going to start plugging things in. So group one here, I'm going to treat as my econ majors because I think the difference had econ, the difference between econ and theater, so econ minus theater. So econ will be my group one, theater is my second group. So we'll take 45,000, right, minus that 33,000. That's what we're centering our confidence interval around, whatever that sample difference we found was. So here, if you want to think about it, our confidence interval should be centered around 12,000, that sample difference that we found. We'll then add and subtract. We'll need to look this up. We'll do that in a second. But the rest of this is just a matter of plugging our values in, right? So 9,000 was the variance for econ majors over the sample size for econ majors. 6,000 was the variance for theater majors over the sample size we had 50 for theater majors. So once I've plugged the values in, the only other thing I need to do to find the confidence interval is get this z value. So I want the z value such that I have alpha total outside of my interval or alpha over 2 on each side of my interval. So I can use that standard normal table, look up alpha over 2 as the area I want in the tail, and figure out how many standard deviations away I need to go or what that z value is. So my alpha was what, 0.05. So I'm going to want to have 0.025 in each tail there. Okay. So at this point, I need to go to my standard normal table or my z tables. I know the area I want in the tail, so I'll look that value up in the middle and then find the corresponding z value. Okay. So z table, let's look up 0.025. So negative 1.96. Okay. Excuse me. Hopefully we're like used to that process. We've been looking at these z values quite a bit. We had the old confidence intervals. It's the same method. Now I found negative 1.96. What I need to remember is that, right, that's already built into my confidence interval equation. When I see that negative 1.96, that's okay. Go 1.96 standard deviations below the sample difference you found to get your lower bound, but then go that same number of standard deviations above, right? Add that value to get your upper bound. So yeah, I found negative 1.96 from the table, but I have to remember that positive negative sign are already built into my confidence interval equation, so I just need to plug in that 1.96. Okay. And then from here, it's just a matter of computation. Okay. Any questions on this one? We'll look at what the actual, if I plug this in my calculator, we get some values. I'll give you some hypothetical ones. So I think the actual number is like, I think I screwed this example up. I think that those variances were supposed to be standard deviations. So we get a really tight window. It's like 11,964 to 12,036, if I can remember these numbers correctly. So it's like a really narrow range for where that difference in starting salaries were. Now, if this is true, right, then the true difference in starting salaries are only positive values. So with 95% confidence, if I'm thinking about what I'm really building is a confidence interval for where that true difference is between econ and theater major starting salaries. So here, if this is my confidence interval with 95% confidence, I can say they make more, right? Econ majors make more than theater majors. So I only have positive values in my confidence interval. If I only had negative values, let's say it was like negative, I don't know, 3,000 to negative 1,000. Well, then what could I say? Well, now with 95% confidence, if this is my confidence interval, what could I say here? If it only includes negative values, it would have to be that theater majors make more. So with 95% confidence, I could say theater majors make more if my confidence interval only included negative values. Here's where it gets a little tricky. What if this was my 95% confidence interval? What can I say? Not much. yeah. I can't really say anything because the true difference could be negative, which would mean theater majors make more. Could be positive, which means econ majors make more, or could be they make exactly the same, or that difference is 0. So anytime I have a confidence interval for these two population examples that only includes negative or only includes positive numbers, I can make some pretty interesting statements, right? I can compare any two majors that I really wanted to, and with different levels of confidence, say that one makes more than the other, one makes less, if I see confidence intervals that look like this. If I see confidence intervals that look like this, I can't really say much at that level of confidence, okay? So this is how we'll start using these confidence intervals, right? They actually have some usefulness. When we get to the proportion ones, it'll be interesting to think about like the difference in proportion of people voting for someone. We can make some pretty cool, I guess cool is a subjective term, but pretty cool statements. So I think I have this like all worked out. We identified the piece of information we were given. We looked up that z value. Then it was just a matter of plugging everything in, getting it entered into our calculator to come up with our lower and upper bound. And then once we had that, we can start to see, can we make some interesting statements about the true difference between these two groups? Okay. Excuse me. All right. So we'll do one more example here. So this one, I'm thinking about robbery rates. So I've got Indiana and Ohio, and I've got this time period, right? Same time period for both. So we're going to treat every year as though it was a observation, right? So my sample size for Indiana and my sample size for Ohio will both be 24. I have 24 years of data from each state. The sample mean that I see for Indiana and the sample mean robbery rate I see for Ohio is what? 109 and 163. And then I'm given this known population variance for each state, which is what? 175 for Indiana, 497 for Ohio, right? That's what was kind of given to me here. Okay. So if I wanted to build a 95% confidence interval for the true difference in Indiana and Ohio's robbery rates, how would I go about doing that? Right. Well, first of all, we'll write down kind of the general form of the equation in our context. So our group one is Indiana. So we'll take their sample mean and subtract the sample mean that we found from Ohio. And that's what we'll center our confidence interval around. We'll then have to look up the number of standard deviations away we need to go to get alpha over 2 on each side of our confidence interval. And multiply by the standard deviation for the difference in those two groups, which is just each group's population variance over that group's sample size. And I'm just using I and O to represent Indiana and Ohio here, kind of using the subscriptions to identify what group. So I just start plugging my values in here. So 109 minus 163. Over here, I've got what? 175 over 24, and then 497 over 24. The only thing left that I need is that Z value. But if I wanted to build a 95% confidence interval, what's my alpha? 95% confidence interval. Alpha is 0.05. Well, that's exactly what we had in the last problem. Anytime I'm building a 95% confidence interval, when I'm using that standard normal distribution, I'm always going to be going the same number of standard deviations away. So alpha divided by 2 would be 0.025. That's what we had in the last problem. So when I go to look that up in the table, I'm going to find the exact same number, which was 1.96. Okay. So if I'm doing a bunch of these problems back to back, if I'm looking at the same confidence intervals and I'm using that standard normal distribution, like the same confidence level, I'm always going to find that same Z value. So you can just use that 1.96 again. Does that make sense? Why I can kind of glossing over that step? But we could go to the table and look it up again. Let's see. So, right, you can scroll down here. 0.025, oh yeah, negative 1.96. That's already built into my confidence interval equation. Add to my upper bound, subtract to my lower bound. So I just need to use that 1.96. And then from this point, it's just a matter of doing some computation. Okay. Any questions on that? I've got a couple more things I want to mention here, but kind of stop here for a second. Any questions? So really all we're doing is plugging in all the information we're given, looking up that Z value. And really, these are the same steps we had for one population examples. It's just we've got twice of everything now. Okay. So if we think about this, what was the sample difference I found? Negative 54. So my confidence interval should be centered around whatever that sample difference is. Just like my old confidence intervals used to be centered around whatever sample mean I found. Well, now I'm looking at the difference in sample mean, so it's going to be centered around whatever that sample difference I found was. So if I'm looking at these possible answers, I can rule D out right away. Right? Now, I need to make sure that I'm careful about making sure I have the ordering correct. Right? It's going to dramatically change my confidence interval. But here, I can rule this one out. But after that, it's just a matter of getting these entered into my equations, doing the computation, and here I've got negative 64 to negative 43. So I've only got negative values in this confidence interval. What can I say with 95% confidence? That Indiana's robbery rates are, yeah, if I've set this up to be Indiana minus Ohio, and the only values in my confidence interval are negative, well, that must mean that the true difference is one of those values. Well, if they're all negative values, it means a true difference is negative, which would imply Ohio's robbery rates are greater than Indiana's. So from this sample evidence, from this 24-year time period, we could say with 95% confidence, Ohio's the worst state. Well, not worse, but we could say their robbery rates are higher, right? Okay. So if it crossed over, like let's say it was negative 64 to 43, right? Where I've got negative and positive values, but also the value of 0. Can't really say much there, because if the difference is negative, Ohio would have higher robbery rates. If it was positive, Indiana would have higher robbery rates. If it was 0, they'd be exactly the same. So anytime I have a confidence interval that kind of crosses over this 0 point, I kind of lose the ability to really make any useful statements. Right? But if it only includes negative or only includes positive values, that's where I can make some interesting statements. Okay? So the video that I'll post in place of Class Friday, since remember we won't have Class Friday, we'll kind of continue to go through these examples, but hypothesis testing. And then on Monday, we'll kind of start 2 population examples for proportions, okay? Working through confidence intervals, hypothesis testing for those. But yeah, I think that's all I've got. If you have any questions over test corrections, remember, I won't be here the rest of this week. So if you want to reach out via email, I can try to answer questions that way, or we can set up a time. I should be Thursday afternoon and most of Friday still available to meet via Zoom if you want to do that. So feel free to reach out. I want everybody to do those corrections and get all the points possible back so that we get that average of the second exam to be right where I want. Okay. All right. We'll see you guys on Monday.